Check this out. We've got something really fun today. This is so amazing. Oh man, again? 9.2 Antiderivatives with initial conditions. Let's review by finding the most general antiderivative of this function here. So we'll call it capital F of x. Now we could consider the natural log here, the natural log of 5, just a constant and ignore it. So that would be in the denominator. And how did we get 1 over x? Well, that would have been the natural log of x. And then we needed plus c for the most general antiderivative. But we could consider the natural log of 5 as part of the original function. And we know that if we had the log base 5 of x, the derivative would give us 1 over x natural log of 5. So either one of these would work. Now, in some questions, we'll be given more information, and then we can actually solve for c. So in this case, the point 0.53 is on the antiderivative. So let's see what c would be. The y value is 3, and the x value is 5. And now we just need to solve for c. So 3 is equal to 1 plus c. That means that c is equal to 2. We want to find the equation for displacement, and in this question, s is displacement. So the derivative of s with respect to t is equal to the velocity. So we want to find the antiderivative of this, and that will give us our displacement equation. So the antiderivative of 2t is t squared, and then we'll have a plus c. In this question, we've been given initial conditions. So they told us the displacement was 3 when the time was 0. So they gave us this point on the graph. So let's put in that point. 3 is equal to 0 squared plus c. Now we can see that c is equal to 3. And now that gives us the equation for displacement is t squared plus 3. We want to find the equations for displacement, velocity, and acceleration. An acceleration is given as a constant 3 meters per second squared. Initial velocity is 4 meters per second, and initial displacement is negative 5 meters. We're going to start off with our acceleration because it's just equal to 3. From there, we can take the antiderivative of our acceleration equation and get the velocity. So the antiderivative of 3 is 3t plus c. Now, because we're working with polynomials, then this c is actually our initial condition, or our initial velocity of 4. But we could always solve for c by putting in the information that we're given. So we'll put in 0 here, and we should get 4. And we can see that c does in fact equal 4. So our velocity equation is 3t plus 4. Now we'll take the antiderivative of velocity to get our displacement. The antiderivative of 3t would be 3t squared divided by 2. And I've got to divide by 2 because I know that when I take the derivative, the 2 will come down and multiply by the coefficient. And I see no sign of it, so I need to divide by 2 to cancel out that 2 that's coming down. The antiderivative of 4 is just 4t, and we'd have a plus c. Now, same thing with this. Since this is a polynomial, then the c would just be our initial displacement. So our displacement equation is 3t squared divided by 2 plus 4t minus 5. We want to find the equation for displacement. If the velocity is 3 meters per second when time is 3 pi over 2 seconds. The acceleration is given, it's cos t, and the initial displacement is e meters. Since we're given the acceleration equation already, we can just take the antiderivative of that to find our velocity equation. So the antiderivative of cos t would be sine t plus c. Now, we're given some information here so that we can solve for c. And that information is the velocity is 3 when the time is 3 pi over 2. Now we know what sine 3 pi over 2 is. That would be -1 at the bottom of our unit circle there. And now we can see that c is equal to 4. So our velocity equation is sine t plus 4. Now we can take the antiderivative of our velocity equation to get our displacement equation. So the antiderivative of sine t is negative cos t. So when we take the derivative of cos t, we'll get negative sine t. We don't see the negative here, so I've got to put a negative here to cancel that negative out. The antiderivative of 4 is 4t, and we're going to get a plus c here that we need to solve for. Now we have initial displacement here, and it's e meters. Now this one is a bit more complicated because it's trig, and so our c value isn't automatically e this time. So let's put in our initial displacement. It's going to be e, and we have negative cos at 0 plus 4 times 0 plus c. Now 4 times 0 is just 0, so that's gone, but negative cos 0 is -1. So c will be e plus 1. So that means that our displacement equation is equal to negative cos t plus 4t plus e plus 1. Some curve passes through the point, -1, 0, and has the derivative of 6x squared plus 6x. Find the equation of that curve. So we just need to find the antiderivative of this. So y is equal to, this is x squared, so it used to be x cubed. Now we know the 3 is going to be coming down here and multiplying by the coefficient to give us 6. So must have had a coefficient of 2 originally. This is plus x squared, same thought process here. We know that 2 is going to come down, multiply by the coefficient to give me 6. So this coefficient must have been 3. And then we get a plus c. But we know that this curve passes through this point. So let's put this information into our equation here and solve for c. So on this side of the equation we just have 0. This side we've got -2 plus 3 plus c. And that just equals 1. Subtract that to the other side. Looks like c is going to equal -1. So the original curve here is y equals 2x cubed plus 3x squared minus 1. Suppose for the graph g that every point's derivative is e to the negative x. We want to find the equation of a graph that is parallel to g that passes through the origin. Now if it's parallel to g, then it's got the same derivative. So to find this curve, we just need to take the antiderivative of e to the negative x, and that would be negative e to the negative x plus c. They also tell us that it passes through the origin, so that's the point 0, 0. So we'll put 0 in for x and y. And we get that 0 is equal to -1 plus c, which means that c is equal to 1. So our curve that's parallel to G and passes through the origin is negative e to the negative x plus 1. A stone is thrown downwards with a speed of 8 meters per second from the edge of a cliff 63 meters high. How long will it take the stone to hit the ground at the foot of the cliff? Now we could start off with our acceleration equation here and say that acceleration is negative. So negative meaning downwards towards the ground. Now we could take the antiderivative of that to get our velocity, and that'd be negative 9.8 t, and because this is just a polynomial, our initial speed here will be our c value. So this speed, though, represents a speed downwards. It was thrown downwards. So this would be minus 8. If it was thrown upwards, it would have been plus 8, because up is represented by positive numbers in our setup here. So we could take the antiderivative of this velocity to get our height at time t. So that would be negative 4.9 t squared minus 8t, and our initial height is 63. So I'm going to say plus 63 is my c value. Now we want this hitting the ground, and that would be height 0 in this model. So I need to solve this quadratic. Now it turns out that this quadratic is pretty messy, and we could get only so far without a calculator. So I'm going to use the quadratic formula, and this is what we end up with here. And if you look at this, we don't want negative time, so we actually don't care about this negative one. We're only concerned with the plus here. So we just want 4.4 seconds. Now we set this up again with negative being downwards, but that doesn't have to be the case. Math doesn't really care about conventions, so we could have set it up saying that our acceleration is positive. Our velocity would then be the antiderivative of this, so 9.8 t plus 8, because these are both working in the same direction. And then we could take the antiderivative of that to get our displacement equation, plus 8t. And this time our initial displacement is just 0. The rock hasn't gone anywhere at time 0, it's at its starting position. So to solve this, we want to know how long it took to travel the 63 meters down to the bottom of the cliff. And we could subtract 63 on both sides, and we would end up with a very similar quadratic as before, just with the signs flipped. But this would yield the same answer as before. You should be able to find antiderivatives with initial conditions. Here's some questions from the textbook. Give them a try. See if you know what you're doing.